What if I told you the materials making up parts of airplanes and even your sports gear could become more eco-friendly using something as simple as, well, weeds or leftover pineapple leaves?
Huh. It sounds a bit out there, but yeah.
Composite materials are in huge demand because they're both strong and lightweight. But the big question is, can we find more sustainable ways to make them? Maybe even by looking at things we usually discard or consider a nuisance.
That's a really compelling question, and it gets right to the heart of a fascinating area where material science is now looking to the natural world for solutions.
Right.
The need for high-performing, lightweight materials isn't going away, so finding a greener path is crucial.
Exactly. And that's what we're diving deep into today. We're exploring the exciting intersection of textile engineering and sustainability. Specifically, we're looking at how adding natural plant and animal fibers can strengthen those polyester composites we were just talking about.
And it's all sparked by a study one of you shared with us, which is fantastic, by the way.
Yeah, great suggestion.
This research takes a close look at 5 intriguing natural fibers. The fast-growing Mikania vine, that fluffy Kapok fuzz, good old wool, the byproduct of sugarcane bagasse,
Right.
and those robust pineapple leaves. Quite a mix.
It really is. So our mission today is to really unpack the key findings of this research.
Yeah.
We want to understand what makes these natural additions so interesting and potentially, game-changing in material science.
Exactly. We're after those surprising facts and those aha moments.
Trying to give you a real understanding without getting bogged down in overly technical stuff.
Okay, so if we step back and look at the bigger picture, the drive towards sustainable development in our, industrialized world makes the increasing importance of natural fibers really clear. These materials offer some really attractive benefits.
Absolutely. They're eco-friendly, they break down naturally, and get this, as they grow, they even pull CO2 out of the atmosphere.
Which is huge.
That's a pretty significant win-win, isn't it?
And it's not just a nice idea on paper either. Natural fibers are already being used in various industries, particularly in more specialized types of textiles.
Which makes perfect sense. And this study isn't happening in isolation, is it? The researchers actually mentioned other cool projects.
They did, yeah. Like using calcium chloride to make wood cement composites stronger and better at resisting water.
Interesting.
It seems like there's a lot of innovation happening in this space.
Definitely.
We're also seeing interesting work using agricultural leftovers like rice husks and bagasse fibers to improve the strength and how easily thermoplastics break down.
Right, using waste streams.
And the use of tiny carbon nanotubes in bagasse and HDPE composites to really boost their strength and resistance to bending. That's another exciting area.
It feels like there's a real push to find more sustainable ways to make and improve the materials we use every day.
There is. And the idea of using special liquids called ionic liquids to dissolve plant stuff to create biodegradable films, that's another fascinating path they touched on.
Okay, but let's zoom in on our main players today. Mikania, Kapok, wool, sugarcane, and pineapple.
Okay, let's start with Mikania. This one's particularly intriguing because it's not something you hear about often in the context of composites.
No, definitely not.
But the study highlights some potential advantages that make it worth a closer look.
Right. It grows like crazy, doesn't it?
Yeah.
To the point where it's considered an invasive pest in many parts of the world.
Exact.
So the thought of actually using it could be a clever way to manage its spread. Plus, it's organic, it renews itself, and it's biodegradable, so it ticks a lot of those green boxes.
What's fascinating here is the potential to turn a problem, an invasive species disrupting ecosystems, into a material solution.
Yeah, turning a negative into a positive.
The study acknowledges that there hasn't been a lot of research on using Mikania fiber in composites yet, but its ability to break down naturally after use makes it really appealing from an environmental standpoint.
And it has quite a backstory. It was first found in Asia way back in 1884.
Wow, that long ago.
Apparently, it might have hitched a ride to India during World War II, maybe as camouflage, or to provide cover for tea plants.
Accidental import.
Now, incredibly, it's ranked among the top 100 most harmful invasive species worldwide.
That's serious. It really makes you think about how we impact our environment and the unexpected consequences of introducing species to new places.
For sure.
But focusing on the material itself, the study mentions it's a lignocellulosic biomass.
Okay, break that down. For those of us who aren't scientists, that basically means it's made up of the stuff that makes plants sturdy, right?
Pretty much, like cellulose, hemicellulose, and lignin.
Got it.
The study found that after they processed the Mikania, the amount of cellulose went up while the other two decreased.
And cellulose is the good stuff for strength.
Exactly. Cellulose is the main structural component in plants, so increasing its concentration can often lead to stronger fibers.
Makes sense.
And the way they got the fibers out sounds surprisingly simple. They collected the vines, soaked them in water, peeled off the bark.
Just peeled it.
Yeah, and then just let them dry in the sun. Pretty low tech.
Huh. Okay, next up is Kapok. Now, I think I've come across Kapok before. Isn't it that really light, almost cotton candy-like stuff?
That's a great way to describe it. It comes from the seed pods of the Ceiba pentandra tree, and its really unique, hollow, tube-like structure gives it some amazing properties.
Like what?
It's a fantastic insulator, incredibly light, and so buoyant it's traditionally been used in things like life vests.
Ah, okay, that makes perfect sense. And the study mentions it's also been used to stuff things like pillows and mattresses because it's so soft and provides good warmth.
Yes, and on top of that, it naturally repels water. It's quite springy, soft to the touch, and importantly, it's biodegradable.
Another sustainable bonus.
Chemically speaking, it's mainly cellulose, with smaller amounts of those other plant components we mentioned earlier, hemicellulose, lignin, pectin, waxes.
So another plant-based fiber with those desirable sustainable qualities. How do they actually get the Kapok out of those seed pods?
The process involves harvesting the fruit before it's fully ripe, then separating the fibers from the seeds in the outer shell, and finally drying them out.
Sounds a bit fiddly.
It can be. What's also interesting is that the study points out that researchers have been exploring different ways to treat and use Kapok.
Oh, yeah.
From chemical modifications to using it as a filler material, even grafting other substances onto it to make it better at absorbing oil, for instance.
So quite versatile then.
It seems like a very versatile material, yes.
Okay, let's move on to something most of us are very familiar with. Wool.
Yeah.
We all know where that comes from.
Indeed. Wool, mainly from sheep, is made up of a protein called keratin.
Ah, keratin. Like in hair and nails.
Exactly. Which contains elements like carbon, oxygen, nitrogen, hydrogen, and a bit of sulfur. What's really interesting about wool is its unique combination of characteristics.
Like that slightly rough surface made of tiny scales and its ability to kind of mesh together, right?
Yeah.
Filter.
That's it, the felting capability. Plus, it doesn't catch fire easily, it can absorb moisture, and it's a great insulator against both heat and cold.
A classic for a reason.
Absolutely. Wool has been used for clothing and textiles for thousands of years, but it has faced competition from synthetic fibers more recently.
Sure.
However, there's a growing interest in wool again because of concerns about the health and environmental impacts of those synthetic alternatives.
A bit of a comeback.
Sort of, yeah. And the study highlights that wool also has potential for more technical uses, like in filters, insulation materials, and even in composites that will eventually break down naturally.
So not just jumpers then.
Definitely not. Its structure, with those overlapping scales and sometimes a hollow core, the medulla, contributes to its unique properties.
No.
And the quality of wool can vary quite a bit depending on factors like the breed of sheep, the length of the fibers, and even the age of the animal.
Right.
The production process basically involves shearing the sheep, followed by carefully sorting and grading the wool based on these characteristics.
Okay, all right. Let's talk about sugarcane. We usually think of the sweet stuff, but this study focuses on what's left after the juice is extracted, that fibrous material called bagasse.
Precisely. And in a country like India, which is a major sugarcane producer, bagasse is a really abundant agricultural byproduct.
Just tons of it left over.
Huge amounts. Chemically, it's rich in cellulose, hemicellulose, and lignin, making it a good candidate for reinforcement because of its crystalline cellulose content.
So that leftover material that might otherwise go to waste can actually be really useful. What affects what it's made of? Does it vary much?
Yeah, several things can influence its chemical composition, including how old the sugarcane was when harvested, where it was grown, the richness of the soil, and even the method used to extract the juice. The study mentions different ways to get the cellulose out of the bagasse using chemicals, physical processes, or a combination of both. They even point out specific pre-treatment techniques.
Okay.
And they highlight that treating the bagasse with an alkaline substance like sodium hydroxide can have a significant effect.
Ah, okay. Here's where it gets really interesting. Apparently, treating it with this alkali can actually make it stronger.
It can, yeah. Stronger and more resistant to bending and impact.
Wow.
But you have to get the amount just right. There's an optimal concentration.
Oh, okay. Too much is bad.
Potentially, yes. The alkali treatment helps to clean the surface of the fibers and can even cause them to separate into smaller strands, which can improve how well they bond with the polyester.
Right, that bonding is key.
Crucial. Key characteristics of sugarcane fiber include its level of crystallinity, how ordered the cellulose molecules are, how fine the individual fibers are, how well they can bounce back after being stretched, and their stiffness, both torsional and flexural rigidity.
Okay.
The process of getting the bagasse involves using both the softer inner part, the pith, and the tougher outer layer or rind of the crushed sugarcane stalk.
So you get a mix.
Which means the fibers you get can be different lengths, yeah.
Uneven. And finally, we have pineapple fiber, or what's often called pina. I know this has a really special cultural connection to the Philippines, doesn't it?
It absolutely does. Pina comes from the leaves of the pineapple plant, which are often just thrown away after the fruit is harvested.
Right. Waste again.
It's a fantastic example of taking a renewable resource and turning what would be waste into something valuable. And you're right, it has a deep history, especially in the Philippines, where weaving pina into fabric is a traditional craft that's been around for centuries.
I actually remember reading about that. It was super popular back in the 1800s. Right?
It was, yeah.
And even though it kind of took a back seat with the rise of cotton, it's making a comeback now.
It is.
They even use it for traditional formal wear, like the pina barong.
The barong Tagalog, yeah.
And it's considered the Philippines' national fabric. That's amazing.
It really is.
Yeah.
And beyond these beautiful traditional textiles, researchers are now looking at using it in more advanced, non-woven materials and a wider range of applications.
So expanding its uses.
Definitely. Chemically, it's mainly cellulose, along with some hemicellulose, pectin, lignin, and other minor components. Similar profile to the others in some ways.
So another fiber rich in cellulose with a lot of potential. How do they actually extract these fibers from the tough pineapple leaves? It sounds difficult.
The traditional method is quite labor-intensive. They harvest the mature leaves, then soak them to soften them up. After that, they manually scrape away the non-fibrous material to reveal the fine fibers.
Scraping by hand, wow.
Yeah. These fibers are then rinsed, air-dried, and finally combed to separate the individual strands.
Takes dedication.
It does. The study even found a direct link between how strong a composite made with pineapple leaf fibers is and how much fiber they actually use in it, the fiber content.
More fiber, more strength. Makes sense. Okay, so we have our 5 natural fibers, each with its own unique story and set of properties. But the real question is, how do they actually perform when you use them to make polyester stronger?
Right. The proof is in the pudding, so to speak. Let's talk about the mechanical tests they carried out. The researchers used a pretty standard method called hand layup to create their composite samples.
Hand layup. Okay.
This involves manually arranging the natural fibers within the liquid polyester resin. Then, they subjected these samples to a series of tests to see how strong and tough they were.
Right. The key tests. Tensile strength.
How much pulling force they can withstand before breaking.
Impact strength.
Their ability to absorb a sudden blow without fracturing.
And bending strength.
Shows how much they can resist being bent or deformed. And they also use something called SAM analysis.
SAM? What's that tell us?
Correct. Scanning electron microscopy. It's like having a super powerful microscope that lets them see the structure of the composites at a microscopic level.
Okay.
This helps them understand how well the natural fibers are distributed within the polyester and how strong the connection is between the fiber and the resin in the interface.
Right, that interface again.
Both of which are really important for a strong composite. Think of it like checking if the reinforcement bars in concrete are evenly spaced and well bonded to the cement.
Good analogy. So, what did they discover when they put these natural fiber composites to the test? Let's start with tensile strength. Which one could handle the most pulling?
The results showed that the composite reinforced with pineapple fiber was the strongest in tension.
Really? Pineapple?
Yeah, reaching a maximum stress of over 42 megapascals. It also showed the most stretch before breaking at over 4%.
Wow.
So surprisingly, pineapple really stood out in its ability to resist being pulled apart.
Wow. Pineapple leading the pack in tensile strength. That's not what I would have guessed at all.
Mm.
What about bending strength? How well did they hold up when pressure was applied?
Again, the pineapple fiber composite came out on top.
No way.
Showing the highest resistance to bending with a maximum stress of over 77 megapascals and a stretch of over 3.7%.
So pineapple's the winner there too.
It seems pineapple fiber is remarkably strong in both tension and bending, at least in this study's comparison.
That's really impressive. Now, what about impact strength? Which composite could absorb the most energy from a sudden hit without cracking?
In the impact tests, Kapok actually performed slightly better than the others,
Kapok's term.
showing a bit more toughness at 1.2 joules. So Kapok seems to be the best at resisting sudden impacts, although the values are generally lower than synthetics.
Okay, so Kapok is the champ when it comes to absorbing a sudden shock. And what did that super-powered microscope, the IMS, tell them about how well these fibers mixed with the polyester? Was it all smooth sailing?
Not entirely. The SIMM images revealed that the different fibers had varying levels of dispersion within the polyester.
Meaning how evenly spread out they were.
Exactly. And the quality of the bond between the fiber and the resin also differed. For some, like Mikania and pineapple, actually.
Even pineapple?
Yeah, they saw areas where the fibers weren't spread out as evenly as they could be, and there were even some small air pockets or voids.
And voids are bad, right? Weak points.
Definitely weaken the composite. This suggests that there's room for improvement in how these materials are processed to get a better, more uniform blend, better manufacturing.
Okay, so we've seen how these natural fiber composites perform on their own. But how do they compare to other materials we know about, like regular cotton, jute, or even those really strong synthetic fibers like fiberglass or carbon fiber?
That's a really important point of comparison. And, well, generally speaking, synthetic fibers like fiberglass, carbon fibers, and Kevlar tend to be much stronger.
Yeah, I figure.
And more resistant to impact than most natural fibers. Carbon fiber, for instance, can have incredibly high tensile strength, many, many times greater than what we saw with the pineapple fiber.
Right. The study mentions carbon fiber can have a tensile strength in the range of 4 to 6 gigapascals.
Yeah.
Which is just...
orders of magnitude higher.
Yeah, vastly higher than our natural contenders. And Kevlar is famous for its exceptional ability to absorb impact.
Exactly. However, the big advantage of natural fibers is their sustainability. That's the trade-off.
All right, the green angle.
They come from renewable sources, they can biodegrade, and often they require less energy to produce compared to their synthetic counterparts. So while they might not be as strong in every single measure, they offer a much greener alternative.
So it's a bit of a trade-off then. You might sacrifice some ultimate strength for better environmental responsibility.
Exactly.
Especially in applications where that extreme strength isn't absolutely critical.
Precisely. The study specifically highlights the potential of pineapple fiber composites in areas like construction and the automotive industry, where their good strength and durability could be really valuable, and Kapok fiber composites, because they're lightweight and can absorb impact.
Right, the impact gen.
Could find uses in later structural parts, soundproofing, insulation, and maybe even in car safety features.
Interesting possibilities. But the study also points out that there are still some hurdles to overcome with these natural composites, right? It's not perfect yet.
No, definitely not. There are still challenges. Things like getting the natural fibers to bond really well with the plastic matrix, that interface issue again. Their tendency to absorb moisture, which can affect performance over time.
Water.
Yeah. The fact that they might not be as fire resistant as some synthetics, and often they're lower resistance to impact compared to those high performance synthetics.
So we probably won't see buildings made entirely of pineapple anytime soon.
Probably not, no.
Yeah.
But for applications where moderate strength and a smaller environmental footprint are important.
Which is a lot of
A
applications.
huge number, yes.
Yeah.
These natural fibers seem like a really promising direction.
Yeah, absolutely.
And the future for composites made with pineapple and Kapok fibers looks particularly encouraging, with ongoing research focused on improving their properties and finding new ways to use them.
The study does mention its own limitations, though, doesn't it?
Yeah.
Like, they didn't try to optimize things like how much fiber they used.
Right, they used a fixed percentage.
And they didn't do really advanced tests. Plus, the hand layup method they used to make the samples isn't the most consistent way to manufacture things on a large scale.
Those are important points, yeah. Hand layup is a good starting point for initial research. It's simple, but it typically results in a lower percentage of fiber in the final composite, maybe around 20–25%.
Okay.
And it can be tricky to get a uniform thickness throughout the material. Quality control is harder.
Right.
More advanced manufacturing techniques like compression molding can achieve higher fiber content and more consistent quality.
So more research and development are definitely needed to really fine-tune these natural fiber composites and figure out how to produce them reliably on a larger scale.
For sure.
But it's exciting to see this initial investigation and what they can do.
It is. The study really underscores the need for future work focused on improving that interface, the bond between the natural fibers and the polyester resin.
Always back to the bonds.
It's critical.
Yeah.
And exploring different and more advanced ways of processing these materials.
So to wrap up this deep dive then, we've uncovered the really exciting potential of using these readily available and in some cases even invasive natural fibers, Mikania, Kapok, wool, sugarcane, and especially pineapple.
Pineapple, the surprising star.
To make polyester composites stronger.
And while they might not always be able to match the extreme performance of some synthetic materials, the fact that they're sustainable and have some unique properties opens up a whole new range of possibilities.
Yeah.
For creating more environmentally friendly products and engineering solutions.
Hopefully for you, our listener, this has given you a valuable shortcut to understanding this fascinating research and maybe even spark some aha moments about the amazing materials all around us, even the ones we might usually overlook, like weeds or fruit leaves.
And that brings us to a final thought for you to consider. Given the surprising strength-to-weight ratio we've seen in some of these natural fibers, like pineapple, and their potential to break down naturally at the end of their life, could we be on the verge of a new era where our buildings and even our vehicles are at least partially made from the plants we cultivate?
And maybe even the plants we consider weeds.
Perhaps. What innovative uses can you imagine for these natural composite materials? Something to think about.